Toward the end of the 19th century, the horseless carriage became a familiar sight in most cities. By then, motive power had been invented to take the place of human beings or draft animals. First came the steam engine, but later on the handier internal combustion engine was adopted. A mixture of gasoline and air is ignited in the cylinder, and the up and down movement of the piston is converted into rotating motion. More efficient internal combustion engines, which will produce rotating motions in a direct manner, have been sought. But meanwhile, the automobile industry developed on the basis of the reciprocating piston engine. In this system, gas is supplied and removed from the cylinder through valves coupled with the crankshaft by a complicated linkage. Such old-fashioned mechanisms are used even today. However, there is now a much simpler system. It started with geometry. Mathematicians knew that when a circle is rolled on its circumference along another circle with double radius, a point within the circle generates a curve called a trochoid or epitrochoid. Now, if you inscribe a triangle within an epitrochoid like this, you are getting close to the basic theory of the rotary engine, invented by Dr. Felix Wankel of Germany. Various other figures can be inscribed in an epitrochoid. But the most effective shape for automotive engineering is the triangle. Let us observe how the triangle moves within the epitrochoid. As the three apexes move uniformly along the curved surface, the area between is divided into three chambers, the volumes of which are constantly changing. At the right is the conventional reciprocating piston engine. In the rotary engine, however, the cylinder is replaced by the rotor housing, and instead of a piston, there is a triangular rotor. The orange-colored part is the eccentric shaft, which acts as a crank. Let us examine the combustion chamber. In the conventional engine, the cylinder volume changes as the piston goes up and down. But in the rotary engine, the volume, configuration, and position of the operating chamber changes as the rotor moves in an eccentric orbit. Let's review the process once again. As you see, the two are completely different. Reciprocating piston engines generally require valves for gas intake and exhaust. The mixture of fuel and air is introduced through the intake port by opening the valve and depressing the piston. When the valve is closed and the piston is pushed upward, the gas is compressed. As it ignites, the piston is forced downward by the explosion. The exhaust valve is then opened, and burned gas is forced out by the rising piston. Gas is taken in again, and the process is repeated. While the shaft turns twice, explosion occurs only once. The rotary engine has no valves. Gas is admitted through the intake port on the side of the housing. The rotor itself acts as a valve. As it turns and comes to this position, gas is brought in through the intake port, previously kept shut by the rotor. When the volume of the operating chamber is near its maximum, the intake port is shut off by the rotor, and the gas is compressed as the chamber becomes smaller. Ignition and explosion. Pushed by the expanding gas, the rotor turns. When it reaches the position of maximum volume, it uncovers the exhaust port and the gas is expelled as the chamber contracts. Again, intake, compression, ignition, and exhaust. Thus, during one rotation, the rotor performs all these strokes. Since it has three sides, the same process is repeated continuously. When side A is about to be propelled by the exploding gas, side B is in the intake and compression stage, and on side C, exhaust is taking place. Then side A goes into the exhaust stage, while side B is expanding, and side C begins the intake and compression cycle. Observe that as the rotor makes one turn, the output shaft makes 3 turns, and ignition and expansion occur 3 times. With the triangular rotor, intake, compression, expansion, and exhaust are performed most rationally and efficiently.